during my presentation, I'm going to be giving pointers to a large number of other websites and also publications. To make life easy for you, I have asked Kishore if he might take a set of links that I prepared ahead of time and share it with everyone in the chat session, if that's possible. So, all right. So in my talk today, I want to go over a number of issues that people run into when they're trying to take artificial intelligence solutions, either AI solutions that are an entire system or a subsystem in part of a larger system, and how do you make them more robust and more safe for application in the broader world. So as Aviral mentioned, I'm a professor of computational media at the University of California, Santa Cruz. And then I have also recently been working as a chief consulting scientist for a AI-led web application testing startup called Autonomic, located in San Jose. Within my group, we've been doing a number of AI-related projects in recent years. I guess historically, one that I've worked on is using machine learning classification to predict where bugs are going to appear inside large repositories of software and be able to predict which changes being committed to those repositories will have bugs in them in the future. I also have a student who's been using neural network techniques in the last 2 years to be able to generate new music that meets a particular kind of sentiment. So if you want to generate upbeat music or downbeat music, are you able to not only generate good sounding music, but music that meets that particular emotional goal? And then finally, I've also been interested in autonomous vehicles, and I have a group where we've been developing a simulation technology or a simulation environment, which we call Cruiseway, that's capable of generating a wide range of scenarios for testing autonomous vehicles. And so these different projects give me different kinds of insight into the sorts of things you need to do to make AI robust and safe. I think it's important to mention as we get going, we tend to use the term AI as if it is this one single monolithic thing. But AI itself is a very broad set of technologies, all of which are maybe unified by a single overarching aspirational goal to the creation of machine intelligence, but they adopt many different approaches. So we have classical machine learning, we have approaches that use neural networks. Some of them are focused more on images, others are focused more on language and language generation. And then what tends to get forgotten in modern uses of the word artificial intelligence are planner-based approaches where you're trying to craft intelligent actions through a very large space of possible actions. And these techniques are still incredibly useful as well. So it's important to realize there is no one AI, there's sort of a lot of AIs. And even though we'll be focusing on a couple broad themes in this talk, it's important to realize that each one of these different areas of AI has its own traditions and own approaches that you would need to use in order to determine safety and robustness and freedom from error. So one question is, what does AI actually look like? And so I thought it would be useful to provide a few pictures of examples of like actual AI systems just to ground our thinking and to give us a few examples to think about. Whenever I am preparing slides, I often will go to Google image search and I'll just type in whatever the thing is I'm looking for. And so in this case, I went to Google image search, I typed in artificial intelligence, and here are a range of the images that came back. And so from these, I can determine a few things. First of all, artificial intelligence is blue. And when it's not blue, it's kind of this like off orangish pink. And it somehow involves like glowing blue printed circuit trace like things. And sometimes it looks like a brain, but not always. Well, okay, I'm not sure. Maybe AI doesn't really exactly look like that. What does AI actually look like? Well, here are some examples. We have with the plants, this is a picture from Plenty, which is a vertical farming startup located in San Francisco. It may look like all they're doing is growing things, but in fact, there's a very sophisticated AI subsystem that is driving the robotics that turns on the lights, determines the frequency spectrum of the lights, determines when nutrients are fed to the plants, and then when it's time to harvest, there's a very sophisticated conveyor belt system that will then carry those plants into a separate room where they're harvested. We then have more familiar kinds of AI, like say Alexa or Siri or Google Voice, where you're able to give natural language commands and get responses back. AI can also be hidden underneath user interfaces that don't look particularly like their AI. So there's a user interface from Spotify and things like based on your recent listening. Well, there's very sophisticated artificial intelligence algorithms underneath the hood that are able to determine, like, okay, what are some other songs that are most similar to the ones that you've seen before. And of course, in the middle, this is one of my favorite historical pictures of what autonomous vehicles and autonomous driving might look like in the future. Okay, so when you are developing an AI system, there's sort of an idealized AI lifecycle that you go through. So you start off with continuous gathering of data. You then use that data to train high fidelity AI models. You then perform some kind of QA testing of that model. Once the model seems like it's working pretty well, you then go ahead and deploy that model out into your real world use situation. And then you have to update those models and continually perform QA on those models as you go along. Every single one of these areas provides opportunities for errors and problems to creep in. And every one of these phases is an area where you need to be focused on how do you either avoid bias or how do you ensure robustness of the outputs from that particular phase. And so this leads to 4 QA challenges for AI. There's many others, but I'll focus on these 4 in the talk here today. So 1, understanding, encountering bias in your data sets. Like a lot of computer science, if you have bad data coming in, you'll have bad data going out. Working and dealing with bias and error in the trained AI models themselves, dealing with mismatch between the training environment and the execution environment, and in particular, dealing with the long tail of just wonderfully weird stuff that can happen in the real world. And then finally, the use of synthetic data generation. Okay, so let's hop into data set bias. So one of the more familiar examples of data set bias is the data sets of facial images or images of people that are then used in training neural networks in order to do facial recognition. There was a recognition a few years ago that these data sets that are currently out there and that are widely used for training facial recognition are quite biased. So here's, I'm going to present 2 tables from a recent paper called Diversity in Faces. It goes into the just how biased are these data sets. Gender and skin color and type. And you can see that there's a very strong bias in this, not just one, but many, many different widely used image data sets. There's a bias towards male images predominantly, and a super strong bias towards lighter skin colors as opposed to darker skin colors. And so as you might imagine, it's going to be much, much harder to make a highly robust facial classification system or facial recognition system when you're looking for darker skins as opposed to lighter skins because your data set is just so biased. In a similar vein, here is the range of age groups in all of these data sets. And you can see, especially, there's almost no images of infants, very, very young infants. And then, once you start getting to, kind of child age 4 to 12, okay, it starts picking up, but there's, definitely the majority of the images are of people who are young adults and adults. And then it kind of trails off as you get older and older as well. And so, as you might imagine, well, if you were trying to do facial recognition for babies, this data set just is not going to work especially well for you. And certainly this is a hard challenge. Those of you who have kids or relatives with kids, I certainly find that even looking back at pictures of my own kids from 10, 15 years ago when they were very, very young, it can be hard to pick out who was who. And so anyway, young babies are a very difficult challenge, and you need to have good data if that is what you are wanting to do. Okay, so how can you address this kind of bias? Well, I think the key to addressing bias in facial recognition data sets or any data set altogether is you just have to understand what are the frequency distributions in your data set. And you also need to have ways of making sure that the data that you collect is highly representative in the first place. It's a combination of having good techniques for bringing that data in the first place, and then you have to go through and you just have to study your data set before you do any training with it whatsoever. Understand your data set and understand the kinds of frequency distributions and the biases that are in there. So this Diversity in Faces project did just that. So they started with images from this large data set from Flickr, primarily in Yahoo, over 100 million images. And then they went through and kind of started working through those images and gathered images, tried to ensure that there was good diversity of the images across many different categories. But then importantly, after a really rigorous ingest phase, they also then did a lot of work to understand the frequency distributions across all of these images. Okay, so once you have your data set, you can then go ahead and train your model. But very often it's the case that even with neural networks, even with highly sophisticated AI systems, there are going to be sources of error in those models. So I'm going to talk a little bit here about digit recognition and use this very famous data set called MNIST. MNIST is a data set of handwritten digits, and the problem or the challenge that you have is, given a handwritten digit, you'd like to be able to understand like what the number is that they were trying to represent. Okay, MNIST is a problem that's been studied for a long time and is very typically used in textbooks that are trying to teach about machine learning and about classification and especially about neural networks. There's one here on the slides that I recommend. It's a great introduction to neural networks. But even the very, very best of a long line of research, it can only get, 9,979 out of 10,000 of these images correct. Why, with years of study and all sorts of effort, why is it not possible to get to perfection? And why is it not possible to get these all the way correct? Well, here on the slide are the images of those 21, the ones that were not able to be correctly classified. And I think by looking at this data, you start getting a sense of like, oh, yeah, like it would be really hard even for a human. Like some of these are just plain ambiguous. They're just poorly drawn figures. And so it's no wonder that the machine learning algorithm is having trouble classifying these. A human would have trouble classifying these as well. So how might you be able to tell this? Well, one approach is to use visualization of your data set. There's a great website, link is down below, where they go through and they do interactive visualizations of many different kinds of this MNIST data set and of how it's being classified. One of the more sophisticated approaches is this one called TSNE. And essentially what it tries to do is each one of these colors is a different digit, and I've written the digit next to each one. And you can get a sense from this, first of all, like, yeah, all the similar digits are pretty tightly clustered together, but within each cluster of digits, you start seeing a different color or a number of dots of different colors. And what that's showing is that for those particular digits, they tend to have qualities that are much more similar to, a one rather than whatever data set or data number that they actually are. So those end up representing the cases that are just plain going to be hard to classify because, you want to get it right, but they have all the properties from another class, even though they're being clustered and clumped together with a different class. So these visualization approaches can give you really good and deep insight into like what's actually going on in your data. And it allows you to understand, get some insight into, well, how is that classification algorithm working and what might be some of the challenges that you're running into. Of course, this is just an entry point into explainable AI and into some of the discussions that we'll be getting in the next panel. So visualization is just one of many techniques for trying to explain what's going on inside an AI subsystem. And there's this entire whole subfield of explainable AI, whose entire goal is to try and give explanations to both the developers, the testers, as well as the operators of AI subsystems as to what is actually going on underneath the hood. Part of that's about trying to understand the models and what's going on inside those models. Other times it can be things like, to an operator, trying to explain to that operator at a high level what's going on or why a system is behaving in a particular way, and trying to bring some of the task context into that so they are not getting flooded with information, but only kind of very specific information about what's actually going on at that moment. And so at the bottom of the slide there's a pointer off to a recent survey of explainable AI techniques that is very approachable. Okay, so you have your AI model, you've gone ahead and deployed it out into the real world. A very common situation that can occur are these mismatches between what you've actually trained on and what actually exists out in the real world. So I'm going to kind of borrow a problem that I learned about from Andrej Karpathy, who is an engineer working on autonomous vehicles. He just recently gave a talk about AI for self-driving. And one of the problems that he talked about in this presentation, the link is on the slides, is this problem of stop sign detection. Now, at face value, stop sign detection might seem like a problem that should be very, very easy for machine vision to tackle. The stop signs themselves have a very regular shape. They have a very predictable color, red, and the lettering on them is also very predictable. And we also generally know about where to find them because they're generally at about the height of a person, and they're generally mounted on poles. So it should be pretty easy to go ahead and find them. And indeed, for stop signs that are reasonably well lit and have all those properties, yeah, it's pretty easy for machine learning to find those. But is it the case that all stop signs are like that? Well, it turns out some stop signs are not red, they're yellow. And then sometimes stop signs are not all the way up, sometimes they're down, down way low. There are some stop signs that are circular and not octagonal, although they are red and they do have the lettering stop. And then to make life even worse, there are some stop signs that have sort of conditional logic applied to them, that in fact, it's not enough just to detect the stop sign to know what to do. You have to detect a stop sign and you have to detect the conditional logic stop sign that's there. And of course, you may be doing testing, even real world testing in a particular situation, and just not run into these. I'm pretty sure that there are none of these stop except for right turn signs in California. I think these are only, at least in the United States, back in the eastern part of the country. So there's this really, really, really long tail of like just wonderfully weird stuff that exists out in the real world. And even though you've done an excellent job inside the lab of doing your training of the algorithm, because of this long tail, you're just going to be running into problems in the real world when you run into these wonderfully weird situations. So part of the challenge in making robust AI is you have to embrace the fact that the real world has these long tails and you have to seek them out and find them. And in fact, if you haven't found those long tails, you should be nervous because they do exist. You just haven't found them yet. All right, so one approach for addressing the long tail is synthetic data generation. So, if you were trying to look for all of the weird and wonderfully weird stop signs in the world, you might have this problem that if you're doing all of your training data in a training or your real world testing, in a small number of cities, well, those cities just may not have certain examples from that long tail. One approach for getting around this problem is the ability to have synthetic data set generation, where you synthetically create the data that you need, and you can simulate this long tail. Now you have to know it exists and know the properties of it to be able to simulate it, but very often it's the case there are data sets that kind of have examples of a lot of these weird situations in them already. So Waymo is in the area of autonomous vehicles, probably the company that's furthest ahead in terms of using this kind of synthetic data approach. They've done a tremendous amount of real world testing. They've driven their cars over 10 million miles, and this is data from 2 years ago. It's very possible it's much, much higher at this point. And that's a big number, but they've driven even more. They've driven over 10 billion miles in simulation. And so this points to many of the benefits of this simulation or synthetic data approach. So even though you can get a lot of data and should do a lot of testing in the real world, simulated data can do this at much, much greater scale, many orders of magnitude more. And again, real world driving, many miles are fairly plain and uneventful. If you want to be generating rare events, well, you need to do those in simulation. And so simulation can just generate, rare events over and over again very frequently. And so the rare becomes very frequent inside simulation. There's a number of different approaches that you can use for synthetic data generation. So capture replay is a very common one. You have some data that you capture from the real world. Maybe it's a rare situation, or in autonomous vehicles, these are often near miss situations or actual hit situations that the driver inside the car who's overseeing the autonomous vehicle, they can press a button and record the last 30 seconds and then replay that. Sometimes there are data sets of real world situations. In the area of autonomous vehicles, they're what they call naturalistic driving studies. And you can get these data sets that have huge amounts of data of cars driving on freeways and in cities and so on. And it's then possible to extract scenarios, testing scenarios out of that naturalistic data. It's also possible to take that same kind of data, but then instead of kind of creating exact scenarios, you just end up extracting behaviors. And so maybe you create like a dumbed down ego vehicle or autonomous vehicle and put those in and create testing scenarios with those. And then the testing scenarios end up coming out sort of through emergent behavior through the actions of all these autonomous agents interacting with each other inside a testing environment. And then finally, if you're testing, say, a vision algorithm, it's possible to create synthetic data by, training generation algorithms on real world data. So one example where this happens is in machine vision for like people's bedrooms or houses. There aren't a lot of good data sets of pictures inside people's apartments and bedrooms. People feel that that's kind of creepy and invasive. So what you do is you have procedural content generation create simulated bedrooms and dining rooms and living rooms and so on, placing furniture, usually models that come from actual manufacturers, and then you're able to use that to train your machine vision algorithms based on that. I guess one of my favorite examples of synthetic data generation is this website where they've trained these very high resolution GANs, generative adversarial networks, on faces, and then they're able to reproduce and recreate very high quality faces from that. So even though all these people look remarkably real, none of these people exist. All of these faces are generated using these generative adversarial networks. Perhaps the easiest way to figure out that they are in fact simulated, the kind of sort of shaded man who's in the upper right-hand corner, if you look very carefully at the edges of his eyes, you'll see like a glasses artifact there. He's not wearing glasses, but there's an artifact that looks like he's wearing glasses. So that's one key there. And I think actually the glasses on the woman in the upper left, I think her face looks a little off as well at the edges of those glasses. So there are these artifacts that can let you tell, but in general, you can see that these synthetic images are extremely high quality and certainly could be used for training machine vision algorithms. All right, well, let me summarize. So the first point, well, make sure you understand your training data, understand its biases. If you're not computing and taking a look at the frequency distributions of your data, you're just going to run into problems because you just don't understand what's going on. Understand why your models are making the mistakes that they do. So, don't just stop at the table telling you, your accuracies and false positives and false negatives. Like really dig in and really try and figure out like what's going on as to why these things are not being classified correctly. What really is going on inside the machine learning algorithm. You're just not going to be able to fix any AI bugs until you really have a good understanding of what's going on. Once you get that out there, the real world has this long tail. So make sure you understand that long tail and feel very nervous if you haven't encountered that long tail yet. And then finally, how can you bring that long tail back in and use it for regression testing and to make sure that things continue to be robust? Well, simulation-based testing is a great approach for doing that, or the generation of synthetic data. All right. With that, that's the end of my talk. Thank you very much. This has been Jim Whitehead lecturing at home.